All right, so welcome back. So it's my pleasure to introduce our second keynote speaker, Professor Ken Carslaw. Ken is a professor of atmospheric science at the University of Leeds. He has published over 250 papers on diverse topics of aerosol, clouds, and climate. He's also the author of the book Aerosol and Climate, and the co-chief editor of the journal Atmospheric Chemistry and Physics. Ken's group developed the aerosol scheme for the UK Earth system model. And most recently, he has been working with statisticians to find ways to quantify, understand, and reduce uncertainty in several aerosol and cloud models. And so today he's going to present on a topic titled Perturbed Parameter Ensembles as a way to understand system behavior and improve models. Welcome, Ken.
Hey, afternoon, everybody. Thank you for the invitation. I was here in 2011, first talking about perturbed parameter ensembles, and they were a really new thing at the time. It was very rare to find people doing this kind of research, and so we really pushed that forward a little bit from about 2011, and it just reminds me how long research takes and how much progress we make slowly through time. Okay, so the thing I'm really talking about here is model uncertainty, and it is a problem for all of us because the reason for most of our research is because we write proposals that say we need to study the uncertainty in something important, air quality or climate. It's almost the standard thing that we put into our proposals. And yet our pathway between the sort of research we do and actual reduction in uncertainty is it's a very bumpy road, and we don't do it very well at all. So over a decade ago, I set about actually tackling uncertainty in our model and really trying to quantify it and reduce it. And this is the kind of research I'm going to be showing you now. So how can we reduce uncertainty in models? So I'm going to be mostly talking about aerosol radiative forcing. It's something that, as again, no one's really explicitly talked about it here, but implicitly in your talking about the radiative effect of aerosols and various things. So it's implied in a lot of our research, the aerosol radiative forcing. So I'm going to assume you at least all know what it is. So it's been persistently uncertain since it was first estimated in the models in the 1990s. The uncertainty really hasn't gone down. So how can we reduce it? Well, we can constrain models, and I'm going to define that word quite carefully later, but basically using observations to find versions of our model that look as much like reality as possible, and eliminating models that don't look like reality. That's what I mean by constraining. We can also make models better in that we add new processes to them to make them look more like reality. That's what I would really call model fidelity. It's not a question of reliability, it's the ability of the model to reproduce reality. So almost everything going on in this room is about making models better, ultimately, and not really reducing the uncertainty as such. And then there are some processes where we have very little knowledge of what's really going on at all, and we still need to make the observations in order to understand how to build the model parameterizations. So we're not really at a mature stage with that kind of research. So understanding processes, for example, in my field, it's about understanding how clouds respond to aerosol. How do clouds respond to aerosol when the humidity is high, when the stability is high or low or whatever? All of these different confounding factors really affecting our ability to sort of disentangle that complexity. So I'm going to try to join all three of these together in one presentation. In particular, the first two. Tuning models and constraining models is often considered to be a separate activity to actually making them better. I'm going to show you that we could actually try to combine those two. If I get time, I'll show you some recent work on exploring aerosol cloud interaction processes, all framed within this idea of perturbed parameter ensembles. But let's just reflect a moment the way that we typically develop models. So we've developed a model called GLOMAP. Probably about 20 years ago now, global model of aerosol processes. It's now in the UK climate model. We first ran the model, having developed it out of the box. It gave us a radiative forcing slightly more negative than -1 watt per square meter. And we thought that's a good estimate. It's somewhere in the middle of what we would expect. And we thought, of course, because our model was more sophisticated than most models at the time, that this was a better estimate of radiative forcing than other models, which were very simplistic. Then we made a new discovery. I can't remember what it was, probably nucleation or something, and the radiative forcing came down. And I said, well, that's a better estimate of radiative forcing because that's a better inclusion of that particular process. So we now have a better model. And then we made another new discovery, and the radiative forcing it became stronger, and then another one, and so on and so forth. And we kept producing new models that had different values of the radiative forcing. And no doubt each time I would then say, write a Nature paper or something and say, this is a very important discovery because it strengthens or weakens the radiative forcing. So this is a little bit how the research goes. I think we all recognize that. Then we produce an entirely new version of that model. You know, think of CAM1 and CAM2. Everything is redone. Now you get an entirely different estimate of the radiative forcing. And then, of course, you make more discoveries. And then there are all the coupled model into comparison project models, which have all been doing that individually, and they all come up with a different answer. And then there's CMIP6, etc. And we'll soon have CMIP7. And I bet it will not look any different to that. Okay, we have a spread of model diversity that's producing a range that we call the uncertainty in radiative forcing. But it's not really a range that we can do anything with, because if you drill down into any one of those models and ask, well, what's your model good at? What's your confidence in your estimate of radiative forcing? And you'll find some of them will be skillful at some things and less skillful at others. And it's very difficult to work out which one of those models or which part of that range that you should trust any more than any other part. Okay, and I think that's the reason the uncertainty hasn't gone down. It's because we are not sampling this the parameter space of the problem thoroughly enough. So our models are now and our natural systems are very much controlled by many, many factors. We all know that. There are so many parameters, even in the individual research areas that we're interested in. Many structures that we can put in our models, many parameters once those structures are in, many environmental conditions that we're trying to understand. The models are expensive to run, and therefore we tend not to run them very much. And we end up with a selection of model results rather than a statistical sample that we can really rely on. So this is where perturbed parameter ensembles come in, and they're really a very simple concept. If you had two parameters which you said were really important for your model, that, for example, the things we've seen here, it could be wildfire emission strength and dry deposition. Okay, there are two parameters in our model, numbers in our model that we put in, dry deposition rate parameter and the wildfire emission strength. Okay, and then we could calculate some model output, let's call it CCN, as a function of those two parameters, and we run the model over the range like that with what appears to be a random selection of model parameter settings. And that essentially is a perturbed parameter ensemble, and it nicely covers that parameter space. The problem is in our models, we maybe have 20, 30, 40 such parameters that we need to understand the effect of, and they all have a combined interacting effect. So really, it's not just two-dimensional, it's probably something like 40-dimensional. So running some simulations like that is not very efficient because the density of points would have to be extremely high in 40 dimensions. So that's not sufficient. What you then do, and this is now, of course, pretty standard technology, you build a Bayesian emulator. In our case, we use Gaussian process emulators, which is just a way of interpolating between these different training points. You're using the model perturbed parameter ensemble to train the emulator in a Bayesian approach. And then you can test it by doing additional simulations in other parts of parameter space and show that your emulator is acceptably good compared to your actual model. So that's what I'm going to show you. You need, what you then have when you have an emulator is you can then, because it's extremely fast, you can then sample it millions of times. And that gives you a high density of points, which you can do statistical analysis on. So I'm not going to say any more about emulators and how we build them. Then observational constraint. So this is what I would interpret to mean as in observational constraint. We're finding the parameter combinations that produce model results that look like reality. So if reality is somewhere in that circle of the observable output from our model, then we want to retain model variants that sit within that circle. Okay, that's constraint. We throw away the other parts, and when we do that, we end up with a subsample of our model perturbed parameters, and we can then calculate a reduced range of the forcing or whatever it is we're trying to calculate. So that's how we go from using perturbed parameter ensembles to using observations to constraining the model. So it seems quite straightforward. We just have to do a whole load of model simulations. We build some emulators. This is all fairly standard now. We then bring in the observations. We find parts of parameter space that are realistic, retain those, and that's our new estimate of the range. So what I'm going to show you is a couple of cases of perturbed parameter ensembles we've done with our global model. And I'll show you, A, that this works. We can reduce uncertainty from some prior estimate of it. And B, it throws up a problem, which is structural uncertainty. And I'll show you how we effectively stumbled on that with this approach. So bringing in observations is, of course, it's not trivial. They're extremely diverse, and they come with their own issues of representativeness and their own uncertainty ranges, etc. They're sparse in space and time in the aerosol world, of course. So what I'm showing you here, this step until bringing in observations wasn't trivial. We used 9,000 observations gridded like that, more than I'm just showing you in those two plots. So that's a very significant step, which I'm not going to go into how we selected and filtered, etc., how we dealt with all of that. But you can imagine it's quite complex. But then if you take the observations and then trying to find that little bit of parameter space that's most consistent with those observations, multiple observations, then we start off with a prior, which is the black PDF of the aerosol radiation interaction forcing. That's what we get if we sample the whole parameter space of the model. And the blue is the part that's consistent with the observations. So this is much more robust than taking a whole bunch of models that have done various things. So we've actually focused down on a part of our parameter space that is consistent with observations. Other parts of that range are inconsistent with observations and we can say are implausible as estimates of the forcing. And of course, we can also generate maps that come with that. We can build emulators of anything we want, global mean values or local values, etc. That looks good, and that is a success, I would say, in that we've built a robust methodology for estimating the uncertainty and then reducing it. And if every model group did that, in CMIP, we would have an uncertainty range around each model, which would be much more useful to us. Okay, so far so good. Then what we did was we said, well, what happens? Are all our observations consistent? If I use just the PM observations, or I just use the aerosol optical depth, or I just use CCM, etc., what do I get? Do they all produce the same estimate of forcing? And unfortunately, they don't. So these are real plots here. These are not just sketches. So when we use PM 2.5 only, then we get a certain value of that forcing. If we use just sulfate, we get a different value of the forcing. So what's the value of forcing? How do I use both of those when they both give different estimates of forcing? So the way I visualize that is we're in two parts of parameter space at the same time. The PM observations tell us we need that part of parameter space, and the sulfate observations tell us we need to be somewhere else. We can't be in two places at once. So there's a compromise going on. So in the previous figure, when I showed you that, that was a compromise. It was taking somehow both sets and saying it has to be fairly good at PM and it has to be fairly good at sulfate, but it's not going to be very good at either of them. Okay, so we had to make a compromise without realizing. So once you start looking at these individual constraints on the model, you realize there's a structural deficiency in the model. There must be. You shouldn't be in two parts of parameter space at the same time. So the reason in this case was actually very obvious. This model didn't include nitrate. So there's a degree of freedom missing here. If we try and get PM right and we've only got sulfate, is one of the big tuning factors in the model, then we're not going to be, that's not going to be a realistic model. So when we put nitrate in, we'll be able to fix that problem, we hope. Okay, so it's an indication that the model has a structural deficiency. Here's another example, this time much bigger PPE, it's 37 parameters. So we're now dealing with 37-dimensional space. And we're perturbing a whole lot of more parameters, not just the aerosol ones, but the cloud and physical climate model parameters as well. And this is some observations over the North Atlantic, the yellow dots, and the seasonal cycle of various things that are very important: shortwave flux, droplet number, cloud fraction, liquid water path. And then the black out to the gray is the range of the PPE. Okay, so it's a huge range. Look at droplet number. It's going all the way from effectively 0 up to 400 per cc, where the observations are down there probably around 100 or so at most. Okay, so most of that parameter space is complete nonsense. So we can throw it away. The thing is, when we do throw it away, does that make our model better at all of the other things? Let's pick on droplet number. So if I constrain just a November droplet number, that blue dot, then all the other months look good as well, which is a really good result. So using just 1 month's droplet number measurements from satellite, we can constrain droplet number throughout the whole year and make it look like the observations. So that's really good to know that the model physics predicting droplet number is consistent throughout the year. We don't have a seasonal bias creeping in or anything like that. So we're in a single part of parameter space there throughout the whole year, which of course is what you would want and expect. If I constrain just droplet number, the model becomes very good at shortwave flux as well, which is very good because this is so important for climate. So constraining just droplet number, we have a very good model of shortwave flux. How many measurements do you need to produce a well-constrained climate model? Droplet number seems to be incredibly powerful. It's thrown away all of those implausible parts of the shortwave flux that the PPE was predicting. So essentially that means we're constraining shortwave flux or constraining droplet number. We're in the same part of parameter space, which is, the model is very consistent, self-consistent, and consistent with observations. However, if we constrain droplet number and then look at liquid water path, that's the integral water through the cloud for these shallow clouds in the North Atlantic, then it's not consistent. So a model that's good at droplet number is not good at liquid water path. Okay, so that is an inconsistency. Again, we're in 2 parts of parameter space at the same time, which we can't be. So this is another structural error in the model, which we are working to try to pin down. But one potential reason is that this model is has what's called single moment microphysics. It just has cloud water mass, not droplet number. So when we remove liquid water, we don't actually remove droplet number. Those two are not properly coupled. If we had a dual moment model, then they would be consistently be removed by precipitation, and that might bring those two into the same part of parameter space. So it's a hint when we've done this that the model is deficient in some way, and it's giving us a hint what that deficiency might be. It doesn't tell you for sure what it is, but you use your knowledge and you can probably find potential good reasons. Okay, then a scary plot. We decided, oh, that looks useful. Finding constraining one thing makes it a bias with respect to the other. Why don't we try all possible combinations? I'm not going to go through what all these variables are, but they're basically taking different months and different variables and different oceans, etc. So down the vertical axis is the thing we constrain. On the horizontal axis, it's the thing we're looking at to see what it's done to it. So every little spot on that carpet is what I showed you in the previous slide. It's the change in the error when we constrain one thing. Okay, so we've reproduced that previous slide probably 100,000 times, something like that now. So anywhere where it's kind of bluey color, that teal color, the model is quite consistent with itself. Wherever it's pink, it's inconsistent. So we're in different parts of parameter space with these different constraints. So we have a whole load of aspects of our model we're now looking at to say why, when we constrain droplet number, does, say, cloud optical depth go wrong? What's it doing? Why is it pulling in different directions? And then we'll go through this process of trying to work out what the structural errors are, and then try and fix them. So what we're effectively doing when we throw all these observations into a constraint without taking care of whether they're consistent like this, is that we're kind of finding an average part of parameter space that's pretty good, but not very good for anything. And that's why the uncertainty remains quite large when we constrain in this way. So we're compromising against all of these observations. So with PPEs like this, I think we can learn something about these sort of structural inconsistencies and then go about fixing them. So if we take just the consistent measurements, the observations which are consistent with each other in the model, then we can constrain the forcing, aerosol cloud interaction forcing, to that yellow PDF, which is narrower than we started with, which is good. Okay, so that's the observations which are consistent with each other. When we start adding more that are not consistent, so they were the pink parts, then we start wanting to be in different parts of parameter space which are not consistent. So we could compress that yellow PDF even further if we could bring those parts of parameter space together and make the model consistent. So that's our task now, is to look at all the ways in which the model is inconsistent and work out why is it inconsistent? What do we need to do to the model to make it consistent? And then try to move all those blobs together into one place. Then we will be able to narrow that uncertainty. So I think we have a path towards really slowly pushing down the uncertainty range in models like this. And considering how long we've been trying to do this, I think that would be a great success. So just to show you what happens when I said we add more observations and then the constraint gets worse. So that's shown as the yellow here. So the yellow is showing as you add more observations along the horizontal axis, you see the yellow dots going up until we reach the peak. That's the point I showed you. And as we add more observations, we start going down again. So the constraint gets weaker and weaker and weaker as we kind of expand out the parameter space and have to make a compromise. Okay, it's surprisingly few observations before we reach that point. So hypothetically, I think if we could remove some of those inconsistencies by improving the structures of our model, we would be able to shift to that purple line, where we would then have more observations that are consistent. So the peak would be further to the right, and the uncertainty would be reduced more because we're getting the power of more useful observations. In principle, if the model had no structural deficiencies, in other words, it was a perfect representation of reality, then we would have the blue. And then the only thing remaining would be observational uncertainty. We can't constrain the model any more than the observations allow us. Okay, so somewhere between the yellow and the blue is where we will get to, because of course we're never going to remove all structural deficiencies. We don't know where the blue is. What is the limit of just having observational uncertainty? What does that mean for the forcing range? No one's ever estimated that. I have no idea how tight that is. Is it plus or minus 0.1 watts per square meter? Is it plus or minus half? I have no idea. But I think we'll be able to get closer to that, something at least approximating that purple line. So that's the topic of a project that we're just starting now in the UK. Right, so that was reducing uncertainty by tuning models and improving them structurally. Of course, the other way, let me just, before I move on, the other way of doing that, of course, is to go into the lab and say, this particular process is uncertain and poorly understood. Let's measure it in the lab and then put it in the model. That, of course, would help. But in the end, models are cannot be built from fundamentals alone. They always have to be tuned against the real world. So lab measurements, et cetera, are going to come into this, but we're always going to have to go through this kind of tuning and structural improvement process. All right, so that's PPEs and constraint of models and structural improvements. I'm going to show you quickly before I end how we can also use them for visualizing cloud behavior. So the parameters that we've perturbed so far have been input parameters to the model, the process rates, etc. The parameters can also be environmental parameters, the things that control the systems of interest. So I'm going to show you a PPE of a stratocumulus cloud, completely different scale, down to now a few kilometers rather than global, using a large eddy model. So here is again our equivalent of what I showed you for CMIP, but in the large eddy simulation world of clouds. This was a really pioneering study from Sandu and Stevens back in 2011. One of the most detailed studies of large eddy simulation of clouds. You know, that's a beautiful picture there of what's coming out of their model. It looks like a cloud. It's got high fidelity. And they then looked at how various perturbations in their model would control that cloud. They changed the sea surface temperature, droplet number, radiation, divergence, etc. So each one of those was changed one at a time. And they said, oh, it makes the cloud thicker. That one makes the cloud transition quicker. That one, you didn't get a cloud. All of these things were done one at a time, which is something that you can get around when you use a PPE. So if we could take all of those and build a PPE of that sort of range of input parameters to the model, the cloud controlling factors, what can we learn? So this is what it looks like when we set that up. So we've built a PPE of a large eddy model with just 85 simulations, so it's really not very much, and it's perturbing these 6 parameters. I'm going to call them parameters, but some of them are more environmental conditions. So PPE doesn't always mean parameter in the model. It can also mean environmental conditions. So the mixing ratio, water in the boundary layer, initial boundary layer depth, inversion strength, inversion change of humidity. Is it dry above the boundary layer or is it moist, etc.? Aerosol concentration, of course. And then one process parameter. So I'm combining those environmental conditions with one process rate. And the one we chose was auto conversion. It's the rate of conversion from droplets to rain. So in principle, you could combine any number of environmental parameters with any number of process rates. So if you plot, then this is what the PPE looks like. If you plot each one against the other, you get a projection essentially of the density of the points. So we then ran the model 85 times and then analyzed these results. So the output is every bit as complex and complicated as the Sandu and Stevens. This is a top-down view of the cloud as it transitions. As the sea surface temperature increases over 3 days, you go from a stratocumulus to a cumulus-like structure. So now we have building a PPE of this. We've essentially run this model 85 times, and we get 85 different cloud evolutions. The difficulty with this, and it's the difficulty with any analysis you would do on a model like this, is how do you define something that you can build an emulator of? What is it I'm building an emulator of? What we decided was to build one of the transition time from stratocumulus to cumulus. So if you plot the cloud fraction as a function of time for all of those simulations, the black line is the mean, the green is all of the simulations. Red is some of the simulations that transitioned extremely quickly for a reason I won't go into. They're all transitioning from cumulus to from stratocumulus to cumulus. So we have to boil that evolution down to one number that we can build an emulator of. Okay, and that's the transition time. And that's easier. That sounds easier than it actually is. So how do you define whether you have a stratocumulus? How do you define when it has reached cumulus? What do you do with the simulations that briefly dip into becoming cumulus, but then recover and become stratocumulus again? What do you do with the natural variability? Every time you run that simulation for exactly the same conditions, you will get a slightly different cloud because of stochastic variability. So all of that is going on and has to be dealt with much more in PPE approach than in single simulations. In a single simulation, you wouldn't have to really deal with all of that. So there's a couple of papers explaining how we dealt with natural variability, etc., which I think was really cool. But in the end, we came up with a definition that it has to get down to 50%. and it has to stay there for a certain time. So your definition really does shape the reliability of your emulator, because you could just have a kind of a point and parameter space that looks a bit odd only because of the way you defined it, not because of what it really was. So it's very challenging dealing with these kind of modeling systems compared to global. So just to give you a snapshot, take all of those simulations and plot them. This is just 2 of the parameters. So you have to remember that each point on there has a different value of the other 4 parameters that I'm not showing. Okay, so just a projection through those 2 parameters. But it does show what you expect. At low aerosol, your cloud transitions quicker because it rains more. And at high autoconversion rate, top left corner, it transitions more quickly because you're inducing rain more easily. So the top is an emulator of the transition time, and you can see in the top left corner, they are transitioning quicker. The bottom is an emulator of the integrated rain, and you can see, again, you get more rain in the top left corner, which explains why the cloud transitions quicker. So by having a PPE, we'll be able to explore this parameter space much more than for example, Sandhu and Stevens' paper, who essentially had one simulation and they perturb one thing, and then back to that baseline simulation, perturb another thing. What's the interaction between those 2 parameters? And here we see aerosol and autoconversion. You get a corner of parameter space that behaves in a certain way. Okay, you wouldn't be able to see that if you just did one at a time. The little gray dots on the left-hand plot are the clouds that didn't transition or had some other problem with them. So bottom right, lots of aerosol and low autoconversion, those clouds never transitioned. Okay, so now we're building an emulator of this system. How do we deal with parts of parameter space that don't have data anymore? Okay, so there's all kinds of challenges in here that I'm not going to go into, but we have, I hope, dealt with. And we can plot everything against everything, really start getting some insight into the various controlling factors. So this is a big deal in cloud feedback, is understanding cloud controlling factors. And now we essentially have, at least in this model, a map of how these cloud controlling factors interact with each other: humidity, boundary layer depth, aerosol, process rates, etc. And we can see various dependencies going on in different parts of parameter space and different controlling factors. So for example, you look at some of these plots and you see straight lines. Contours are straight. So the emulator thinks those 2 parameter effects can simply be combined as if you had 2 one-at-a-time simulations and put them together. Okay, so if the contours are straight, then you don't really need an emulator. You can just do 1-at-a-time simulations and then take the mixture of the 2. So the ones we're most interested in is where the emulator thinks there's some curvature. So you can see in the second row up from the bottom, there's curvature in there. Okay, so you wouldn't be able to predict the model output from taking combinations of 1-at-a-time simulations. So this is really where perturbed parameter ensembles become really useful in being able to understand the interactions. So curvature on here means these 2 things are interacting to affect the output. Okay, so just to summarize then, so perturbed parameter ensembles can be used to train emulators, which enable multiple factors in models to be explored. And this is being done now for a whole load of different systems and different groups, etc. Certainly not by any means just us. I think they provide, I have to risk what I'm saying here, but I think they provide physical insight rather than just trained ML machine learned models. A lot of machine learning doesn't give physical insight. It builds data algorithms that can be used to predict the system, but often with lacking physical insight into what's really controlling what. But when you have something like this, you have a lot of physical insight into what's causing the various behaviors that you see here. So I like PPEs for that reason, that they retain physical insight, which I find very interesting. I've shown that PPEs can be analyzed in a way to expose structural deficiencies. So this is important, and the reason is that almost every time I've ever talked about PPEs, the first hand will go up and say, yeah, this is all very well, but what use is it if your model it has structural deficiencies in? All you're doing is tuning a model that is essentially incorrect. So we've got thinking about that. And our solution is what I've shown you here, that we can use the PPE to expose the structural error. Okay, so now we have to go through this loop, fixing the structural errors and then going back and building a new, smaller PPE. So what I've shown you is different observation types, but we've also looked at, and we see, for example, that the model is good in the summer, but bad in the winter. Can't have a model that's, so if I tried to build a model that was reasonably good in the summer and winter, it would be a compromise model. So I need to fix that. Why is it good in the summer, but not in the winter? Why is it good in the North Atlantic, but not the Southern Ocean? The physics shouldn't be different. So why is the physics deficient in my model? That means the North Atlantic doesn't look like the Southern Ocean. Okay, so we're seeing all these kinds of inconsistencies, and we can slowly, I think, work on each one of them and make the model structurally more realistic. So I've shown that these parameters can also be environmental drivers, and this is a big deal in cloud physics and these cloud controlling factors. And we're gaining a lot of insight into exploring these sorts of nice sort of maps that I showed you. So if you're interested in PPEs, there is a bit of a community now around them. And we had our first peer workshop supported by WCRP that, earlier this year, analysis of PPEs and atmospheric research. People there doing, aerosols like we are, chemistry, clouds, climate, meteorology, severe storms, etc., all kinds of things across all scales. So there's a lot of really interesting research going on, people exposing more and more about their models. Okay, I'll leave it there. Thank you.
Thank you. Any questions for our speaker today? Davin?
Thanks, Ken. Great talk. And probably, as you predicted, your first question from the audience is about model error. Yeah, I was interested to see what you were showing about how the addition of more and more observations doesn't necessarily lead you to an unbiased estimate. And I think by analogy and kind of parameter estimation that like NWP does, if you have a biased forecast model, the addition of more observations doesn't lead you to a better forecast. Until you start to quantify your model error statistics. And so, you're saying that this is a mechanism to reveal the structural error. And you can fix that by fixing the structural uncertainty in your model. And so I wonder, by analogy, could you also fix this by knowing the statistics of the model error rather than perhaps the structural error itself? Because that's sort of what NWP has shown. If you know the first two moments of the statistics of your model error, even if you don't know the physical process of giving rise to that, then you can arrive at a system where you have an unbiased estimate as you increase your observations.
Yeah. So we're, this is quite brain bending in so many dimensions. We have so many parameters that are controlling that error. So we're trying to find ways of boiling it down and extracting the key information as efficiently as possible. So one thing we've done is to work out in which direction do we need to move in parameter space to fix that error. So if we had to bias correct, simply what would we have to do? So would we have to shift our parameters to a part of parameter space that isn't reasonable anymore? So we have a huge amount of information there to guide us, and so to bring these two models observations into consistency, we would have to shift the deposition rate way up. What is that telling us about what's the cause of that? So for all of these errors, we know where we have to go in parameter space, and what that can really give us a clue what's going on. Yeah. So we have a lot of statistical information that's working out what to do with it. And this is a massive big data problem as well. So if people have ideas how we use what we've got here to go that next step, I'd like to have these conversations, because we have some ideas, but definitely not complete.
I'd like to ask a question, if that's okay. So as you were speaking about model uncertainty, I was thinking about the observations that you're using, and how do you deal with the fact that there's obviously uncertainty in those observations? And has there been any time when, in the case of this process, you've kind of diagnosed uncertainty in the data set that you're trying to use?
Yeah, really good question. So it's very difficult to distinguish observational error from structural error in the model, for example. When the model doesn't look good, is that the model or is it the observation? So yeah, we have to pay really close attention to what we think is the observational uncertainty. And the main thing really is the representativeness. So there's some observations are made in locations that isn't fair to compare to our model. They're made near a point source or something like that. Okay, so we have to find a way of filtering those out. This is where I think machine learning could become really useful for kind of working out which observations are representative and useful and others not. But if you look back at some of our previous papers, we really struggled to know how we deal with that observational uncertainty. And mainly it's in the representation error, not in the instrument heterogeneity of where the measurement was made, etc. Yeah, it's an enormous problem. Having more context to where observations are made and would be useful as well.
Thanks, Ken, for a really nice talk. I enjoyed it a lot. I have to say first that I couldn't agree more from your second bullet point there. The work that we have been doing with perturbing the model physics showed us exactly that we really learn. It's not like we make a better model or we fake that we make a better model. My question is, CMIP 7 is brewing right now. Maybe it's time for a PPE MIP.
Yeah, this discussion and part of came out of that peer workshop. There is some discussion. There will be a virtual meeting in January to discuss PPE MIP, I suppose. Yeah, maybe that would be called. Right. Yeah, I mean, the number of modeling centers that have an appetite for something of this scale is quite small. So we're writing an article at the moment about the competing pressures on model compute time. Should we run PPE? Should we run higher resolution? Should we run meteorological ensembles? Should we improve complexity? There's 4 competing pressures on model runtime. Where should we put our resource? And I think we should put more into this kind of sampling of model uncertainty instead of this repeated, my best model goes into CMIP. It's your best model, but it's surrounded by a big uncertainty range. What is it? It's ridiculous way somehow to do science, isn't it? Not knowing the uncertainty around an estimate that you've provided to an assessment. So I think moving towards higher resolution, for example, is going to provide certain information, but with a model that can only be run once for a short time. I mean, it will tell us something, but it won't give us everything we need. So I would be really keen to see a PPE MIP. I can't imagine how we all sit in a room and agree on what the 37 parameters are, mind. I mean,
I would advocate to the GIS management to participate in that.
Was that a question? No.
To follow up on that, it was really fantastic. I'm curious if you had to speculate as to the results of a PPE MIP. Do you think that all of the models in terms of the uncertainty bands that people would report would actually overlap? Or would we see that models suddenly have uncertainty bands but they still don't overlap? And so how do we choose between them? And I know we don't know until we do it, but
I don't know. I really don't think they would overlap. But so there have been 2 PPEs of opportunity perturbing broadly similar things in France and the UK Met Office. Pretty much the same sorts of parameters, but the same exact parameters don't exist in the 2 models, so they can't do exactly the same PPE. But when they compare, they really already start finding issues with their model. And I think that could be the most valuable thing, a little bit like we're showing you here with the detecting structural error. Just simply comparing 2 PPEs immediately exposes issues with one or both of the models. That could be the most valuable contribution to CMIP, to to start exposing some of these deficiencies, and then we can start to weight some of these models. How much do we really trust them, etc. So I think that's missing from CMIP. We have very little to go on. No, but the PDFs are not going to overlap, unfortunately. But we might be able to make them overlap if we each chose different parts of parameter space and consistent with observations. That would be fun to try that.
Ken Duncan here. Thanks for the really nice talk. I just wanted to briefly take that opportunity to plug an Aerocom effort that Leighton and I and others have been trying to push for a while, where we get the models in aerosol space or cloud space or both, even just 3 parameters, just 3 parameters, 30 simulations. It's not a huge lift, but just having those conversations and getting that going would be
and that was
a
challenging,
good
wasn't
start.
it? To choose 3 parameters that are common to what we'd have 4 or 5 models. It was very difficult, wasn't it? So doing that across an entire climate model simulation will.
More questions? I've been checking the Slido. There aren't any from online.
Yeah, thanks for a very nice talk. I was wondering, you showed the example that, in one case you were missing nitrate aerosol, for example, and that was kind of the clue of, how you kind of find the right spot in the parameter space. So having done that many times now with different things, I was wondering how often is it an actual, like a structural inconsistency that you find? How often is it a missing process of sorts? How often do you just find a bug in the code? Or perhaps maybe a bug or a mistake in how you define a process or parameter, like you mentioned, stratocumulus to cumulus transition. Like, how do you find exactly when it transitions to being a cumulus? Like, what's kind of the range of these different options that you have to explore?
Yeah, I don't know. We haven't done it yet. This is at this stage speculation what the cause is. We haven't gone through that loop of actually trying to fix what we think it is. But yeah, building a PPE has already exposed many bugs. That is one good thing. And finding these inconsistencies and going to the Met Office and saying, did you know that they are inconsistent, immediately is, oh yeah, no, that shouldn't be the case. Why is that? Is it the observations you're using? Is it this? Is it that? So immediately, engages people in a discussion about how good their model is, because they don't expect that to be inconsistent. They think their clouds are consistent with the observations they have. But so yeah, complicated conversations and thinking and discussions about the causes and then trying to fix them. I don't see a quicker way. It could be bugs, it could be deficiencies, it could be missing processes. Many options, maybe.
Further questions and discussion? Okay, with that, let's thank Ken one more time. Okay, thank you, everybody. I think this concludes our program for today, and we'll be back here at 8 o'clock tomorrow, right? For the final.